Today we are going to learn about mastering ReLU variants in neural networks. We will explore the significance of ReLU and its variants, understand their role in addressing the vanishing gradient problem, and learn how to apply them effectively to optimize neural network performance. By the end of this video, you'll be equipped with practical skills to enhance your model's capabilities.
Welcome to our video on mastering ReLU variants in neural networks. In this introduction, we'll explore the basic concept of the rectified linear unit, commonly known as ReLU. ReLU is an activation function used in neural networks that has become the default choice due to its simplicity and effectiveness. It introduces nonlinearity into the model while avoiding the vanishing gradient problem that plagues traditional sigmoid and tanh functions. By converting negative values to zero and keeping positive values linear, ReLU accelerates convergence and improves performance in deeper networks. Understanding ReLU sets the stage for exploring its variants, each designed to address specific limitations and enhance model performance.
Now that we have a foundational understanding of ReLU, let's dive into its variants. ReLU variants have been developed to overcome certain limitations of the standard ReLU activation function. Among the most notable are Leaky ReLU and Parametric ReLU, PReLU. Leaky ReLU introduces a small slope for negative values, preventing neurons from dying by allowing a small, non-zero gradient when the unit is inactive. Parametric ReLU extends this by making the slope a learnable parameter, thus providing even more flexibility. These variants share a common goal: enhancing model robustness by reducing the risk of dead neurons, which can severely impact the training of deep networks. Understanding these variants' subtle yet significant differences is crucial for leveraging their strengths in various neural network architectures.
Leaky ReLU is a simple yet effective variant of the traditional ReLU activation function. Unlike ReLU, which outputs 0 for all negative inputs, Leaky ReLU allows a small, non-zero gradient for negative inputs, typically defined by a small constant, such as 0.01. Mathematically, it can be expressed as fx equals x if x greater than 0, else fx equals alpha x, where alpha is a small constant. This minor modification helps prevent the dying neuron problem, where neurons can sometimes become inactive during training and stop learning altogether. By allowing a small gradient pass-through, Leaky ReLU maintains some level of activity in all neurons, making it particularly useful in deep neural networks where many layers can be prone to this issue. Leaky ReLU's simplicity and effectiveness have led to its widespread adoption across various deep learning architectures.
Parametric ReLU, or PReLU, takes the concept of Leaky ReLU a step further by introducing a learnable parameter for the negative slope. This means that instead of having a fixed small gradient for negative inputs, the model can learn the most appropriate slope during training. The PReLU function can be expressed as fx equals x if x greater than 0, else fx equals a x, where a is a parameter learned during the training process. This adaptability allows PReLU to adjust the activation function dynamically, potentially leading to better performance in complex models. By enabling the model to determine the optimal slope, PReLU provides greater flexibility and can lead to improved convergence rates and model accuracy. The effectiveness of PReLU in various deep learning tasks highlights its significance as a powerful tool in neural network design.
The dying neuron problem is a significant challenge in training deep neural networks. It occurs when neurons in a layer output 0 for all inputs, effectively becoming inactive and ceasing to contribute to learning. This often results from the use of standard ReLU, which outputs 0 for negative inputs, leading to neurons that never activate if they initially receive negative inputs. ReLU variants like Leaky ReLU and PReLU offer solutions by ensuring that neurons maintain a small but non-zero gradient, even for negative inputs. This prevents neurons from becoming dormant and allows them to continue learning throughout the training process. Addressing this problem is crucial for deep networks, as the loss of active neurons can severely impact model performance and convergence. By incorporating ReLU variants, we can enhance the robustness and reliability of deep learning models, ensuring that all neurons contribute to the network's learning capacity.
In this section, we conduct a comparative analysis of ReLU and its variants, Leaky ReLU and PReLU. Each serves a unique purpose and comes with its own set of advantages and limitations. Standard ReLU is simple and effective, making it suitable for a wide range of applications. However, its limitation lies in potential neuron inactivity, which Leaky ReLU addresses by allowing a small, constant gradient for negative inputs. PReLU offers additional flexibility by learning the slope of negative inputs during training, potentially improving performance in more complex models. Performance metrics such as convergence rates and accuracy can vary depending on the chosen activation function and the specific architecture of the network. Factors such as the depth of the network, type of task, and computational resources can all influence the decision to use a particular ReLU variant. Understanding these dynamics helps in selecting the most appropriate variant to optimize model performance effectively. Implementing ReLU variants in TensorFlow is straightforward and provides significant benefits in optimizing neural network performance. TensorFlow, being one of the most popular deep learning frameworks, offers built-in support for various ReLU variants. To implement Leaky ReLU, you can use the tf.keras.layers.leaky ReLU layer, specifying the desired alpha value. For parametric ReLU, you can define a custom layer or use available extensions that allow the parameter to be learned during training. Integrating these activation functions into your network involves specifying them in the layer configurations, allowing you to harness the advantages of these variants. By utilizing ReLU variants, you can prevent issues like the dying neuron problem, enhance model robustness, and achieve faster convergence. Optimization strategies include experimenting with different alpha values for Leaky ReLU or allowing the model to learn the most appropriate parameters for PReLU, ultimately leading to improved overall performance. In PyTorch, implementing ReLU variants is both intuitive and effective for enhancing neural network models. PyTorch provides modules like nn.leaky-ReLU and nn.PReLU, allowing easy integration into your model architecture. To implement Leaky ReLU, you can simply use nn.leaky-ReLU with a specified negative slope. For parametric ReLU, use nn.PReLU, which allows the negative slope to be a learnable parameter. Integrating these into your neural network layers involves defining them in the forward pass of your model class. The use of ReLU variants in PyTorch can prevent neuron inactivity, improve model stability, and lead to better training outcomes. Fine-tuning the parameters, such as the negative slope for Leaky ReLU or the initial value for PReLU, can further optimize performance. Leveraging these activation functions within PyTorch's dynamic computation graph framework provides flexibility and control, making it a powerful choice for deep learning practitioners. Selecting the appropriate ReLU variant for your neural network model involves considering several key factors. The complexity of the task, the architecture of the model, and the computational resources available all play crucial roles in this decision. For simpler tasks or models where computational efficiency is paramount, standard ReLU may suffice. However, for deeper networks or tasks prone to neuron inactivity, Leaky ReLU or PReLU might offer significant advantages. Leaky ReLU simplicity and effectiveness make it a popular choice for many applications, while PReLU offers additional adaptability by learning the slope parameter during training. Balancing the trade-off between simplicity and performance is essential, as is considering the impact on both training and inference times. Guidelines for selection include evaluating the specific requirements of your model, running experiments to compare performance, and choosing the variant that aligns best with your objectives and constraints.
In this case study, we explore the application of ReLU variants in image classification tasks, a domain where activation functions play a pivotal role in model performance. Image classification models, particularly those using convolutional neural networks, benefit significantly from the use of ReLU variants. By integrating Leaky ReLU or PReLU, these models can achieve improved accuracy and convergence rates, addressing challenges such as the dying neuron problem. Our analysis involves comparing the performance of standard ReLU, Leaky ReLU, and PReLU in a typical image classification dataset. Results show that models using ReLU variants outperform those with standard ReLU, with PReLU offering the most adaptability and performance improvement. The case study highlights the practical benefits of using ReLU variants and provides insights into their impact on real-world tasks, reinforcing their value in optimizing neural network models for image classification.
As neural network architectures continue to evolve, so too do the activation functions that drive their performance. Future trends in ReLU-based activation functions point towards the development of new variants that offer greater flexibility and efficiency. Researchers are exploring novel approaches to address limitations of current variants, such as improving adaptability to diverse datasets and reducing computational overhead. Innovations in activation functions aim to further enhance model robustness, speed of convergence, and generalization capabilities. The ongoing research into ReLU variants and their applications is set to have a significant impact on the future of neural networks, enabling more sophisticated and capable models. As the field progresses, staying informed about these emerging trends and developments will be crucial for anyone looking to leverage the full potential of activation functions in neural network design.
In conclusion, mastering ReLU variants in neural networks involves understanding their unique characteristics, applications, and impact on model performance. We discussed the significance of ReLU and its variants, such as Leaky ReLU and PReLU, in addressing the dying neuron problem and enhancing deep learning models. Practical implementations in TensorFlow and PyTorch demonstrate their versatility and effectiveness in real-world scenarios. Choosing the right ReLU variant depends on various factors, including task complexity and model architecture. As we look to the future, ongoing research and innovation in activation functions promise to unlock new possibilities in neural network design. Thank you for joining us in this exploration of ReLU variants, and we hope you feel empowered to apply these insights to optimize your neural network models.